Section: Introduction. In this section, we will discuss diffusion models, DMs, and consistency models, CMs, in the context of visual content generation. DMs transform a data distribution into a known prior distribution using a stochastic differential equation, SDE, and are trained to denoise noisy observations. Generating samples from DMs can be slow due to the curvature of the diffusion sampling trajectory, requiring many model evaluations. Various techniques have been proposed to speed up this process, but they often compromise sample quality. CMs, a newer type of generative model similar to DMs, aim to generate high-quality samples more efficiently by ensuring all points in the sampling trajectory map to the same initial data point. However, training CMs can be time-consuming and challenging compared to DMs. Our work introduces a more efficient approach for building CMs. We redefine the consistency condition as a finite difference approximation of a specific differential equation, termed the differential consistency condition. Training CMs directly with this condition as a loss function poses challenges, which we address by employing specific strategies. By viewing DMs as a special case of CMs with a relaxed form of the consistency condition, we can transition smoothly from DMs to CMs by progressively tightening the consistency condition during training. This approach, called easy consistency tuning, ECT, allows us to construct a consistency model from a pre-trained diffusion model, significantly reducing training costs. ECT outperforms existing methods in terms of sample quality on datasets like CIFAR10 and ImageNet 64x64 while using minimal computational resources. Even when considering the pre-training phase of the diffusion model, ECT is much faster than the current state-of-the-art method, ICT. Additionally, ECT reduces the inference cost significantly compared to pre-trained score SDE, DMs while maintaining comparable sample quality. Section Summary. In this section, we introduce diffusion models, DMs, and score-based generative models, SGMs, that transform data distributions to known priors using stochastic differential equations, SDEs, for denoising noisy observations. While DMs require numerous model evaluations for sampling due to trajectory curvature, consistency models, CMs, offer faster generation by mapping all sampling trajectory points to the same initial data point, achieving high-quality samples in just 1 to 2 evaluations. Our proposed easy consistency tuning, ECT, method streamlines CM training, enabling efficient transition from pre-trained DMs to CMs with significantly reduced training and inference costs while maintaining high sample quality. Section: Consistency Models. In this section, we build upon the phosphorus monofluoride ode in equation, Kara's ode, to create consistency models, CMs. These models establish a connection between data distribution and noise distribution through a bijective mapping. CMs aim to learn a function f, x, underscore t, t, that can transform a noisy image, x, underscore t back to its clean version, x, underscore 0. It's important for this function to meet the boundary condition at t equals 0. Previous studies achieve this by parameterizing the CM using theta as the model parameter, f underscore theta as the network for training, and time-dependent scaling factors c underscore text skip t and c underscore text out t, ensuring c underscore text skip 0 equals 1 and c underscore text out 0 equals 0. This setup guarantees the boundary condition is satisfied. Specific choices for c underscore text skip t and c underscore text out t are discussed in Sec. Experiment details. During training, CMs divide the phosphorus monofluoride ode into N1 subintervals with boundaries at t underscore text min equals t underscore 1 less than t underscore 2 less than L dots less than t underscore n equals t. The model is trained using a CM loss that minimizes a metric between neighboring points on the sampling trajectory. This loss involves a metric function d, CDOT, a trainable neural network f_theta to learn the consistency function, an exponential moving average f_theta caret of past f_theta values, and a calculation involving the image data. The curriculum for discretization, denoted by N, should be adaptable and adjusted during training for optimal performance. In a key study, a metric function called Learned Perceptual Similarity Score, LPIPS, is used. Weights W, T_I, are set to 1, and sampling times T_I are determined based on a specific formula. The score function nabla_x_t log p x_t can be estimated from a pre-trained diffusion model, resulting in consistency distillation, or using an unbiased score estimator, resulting in consistency training. A subsequent work, ICT, enhances training efficiency and CM performance by introducing improvements like replacing LPIPS with a pseudo-Huber metric, eliminating the EMMA component in f_theta caret, adjusting the weighting scheme, carefully selecting scaling factors, and implementing a sophisticated training curriculum. This curriculum involves various parameters and a specific sampling method from a discrete log-normal distribution. Moving on to easy consistency tuning, ECT, we will introduce the core concept of the differential consistency condition for training CMs and derive a corresponding loss objective. We will then discuss the challenges associated with training CMs using this approach and present our method, ECT, as a simple and effective way to train CMs to meet the consistency condition efficiently. The resulting CMs from ECT can produce high-quality samples in just 1 or 2 sampling steps. Section Summary. In this section, we delve into consistency models, CMs, which are founded on the phosphorus monofluoride ode, establishing a mapping between data and noise distributions. CMs aim to learn a consistency function that restores noisy images to their clean versions, ensuring a boundary condition at t=0 is met. We discuss the training process involving discretization of the phosphorus monofluoride ode, loss minimization between adjacent points, and the adaptive curriculum for achieving optimal performance. Additionally, we introduce easy consistency tuning, ECT, as a method to efficiently train CMs by focusing on the differential consistency condition, ultimately enabling high-quality sample generation in just a few steps. Section: Differential consistency condition. In this section, we learn about the differential consistency condition. We start by understanding that consistency models, CMs, learn a function that maps a noisy image back to a clean image. We can define CMs by looking at the time derivative of the model output. The time derivative of the clean image is 0, but just having a derivative of 0 is not enough to ensure the model matches the clean image. We need to set a boundary condition to make sure the model output aligns with the clean image when there is no noise. To learn this consistency condition, we use a finite difference approximation. This involves creating perturbed images at different noise levels and minimizing the difference between the model outputs of these images. We also introduce a loss function that includes a weighting function and a metric function to train the CMs effectively. However, there is a challenge known as the curse of consistency when optimizing the model as the noise level approaches 0. This is because errors accumulate as we divide the noise horizon into smaller intervals, affecting the training convergence. The trade-off between the number of intervals and the maximum error plays a crucial role in determining the prediction accuracy of the model. If not managed properly, the model may struggle to minimize consistency errors and lead to poor prediction performance. To address this issue, we conducted experiments with different numbers of intervals to observe how the model training is affected by the accumulated consistency errors. The results confirmed that training the model with very small intervals can cause it to get stuck due to the increasing consistency errors. This highlights the importance of balancing the interval size during training to prevent performance degradation. Section Summary. In this section, we introduce the concept of the differential consistency condition for contrastive models, CMs. Instead of solely relying on the time derivative of the model output, we enforce a boundary condition where the model output matches the clean image when the noise level is 0. By minimizing the distance between perturbed images at different noise levels, we ensure that the model remains consistent with the clean image, addressing the challenge of slow training convergence or divergence as noise levels approach 0. Section: Tackling the curse of consistency. In this section, we tackled the issue known as the curse of consistency. We discussed how training continuous models, CMs, from scratch with a specific loss objective could lead to training instability when the time step, delta t, is very small. However, we can overcome these challenges by making smart design choices. One strategy we recommend is to begin training CMs with a pre-trained diffusion model. By starting with a large delta t and gradually reducing it to 0, we can smoothly transition from denoising diffusion models to continuous models during training. This approach is like a gradual shift from models with delta t equals t to models with delta t equals delta t. Pre-training with a diffusion model can be seen as a form of consistency training with a less strict version of the consistency condition. Additionally, we propose using a continuous time training schedule that starts with diffusion pre-training. Unlike other training schedules, we divide the training into overlapping intervals to factorize the probability distribution and enable continuous sampling of time values. To control the reduction of delta t during training, we introduce a mapping function that depends on the training iterations. This function ensures a smooth transition from diffusion pre-training to continuous training. Furthermore, we discuss the choice of metric for evaluating model performance. We opt for the squared L_2 metric used in diffusion models and explore different adaptive weighting terms to improve training efficiency. By decoupling the weighting function from the mapping function, we introduce adaptive weighting that helps prevent gradient vanishing issues and numerical instabilities during training. This adaptive weighting, combined with regular weighting, enhances the training process by controlling gradient variance across different noise levels. Overall, our strategies aim to address training instability issues and enhance the efficiency of continuous models by making thoughtful design choices in model initialization, training schedules, and metric weighting functions. Section Summary. In this section, we address the training instability issue known as the curse of consistency when training continuous time models, CMs, from scratch with a specific loss objective. By employing strategies like starting with a pre-trained diffusion model and implementing a continuous time training schedule with overlapped intervals, we can mitigate these instability issues and enhance the efficiency of CMs. Additionally, by carefully choosing metrics like the pseudo-Huber metric and weighting functions that control gradient variance, we can further optimize the training process and improve the generative capability of CMs. Section: Experiments. In this section, we conduct experiments to assess the efficiency and scalability of ECT using two datasets, CIFAR10 and ImageNet 64 x 64. We measure sample quality using Frechet inception distance, FID, and Frechet distance under the DINOV2 model, FD_text DINOV2, and evaluate sampling efficiency based on the number of function evaluations, NFEs. Additionally, we compare the relative training costs of these methods. Detailed implementation information can be found in Sec. Experiment Details. We compare CMs trained with ECT, ECM, against various diffusion models with advanced samplers, distillation methods like consistency distillation, CD, and improved consistency training, ICT. The main outcomes are summarized in Fig. Efficiency, showcasing the training flops, inference cost, and generative performance of the four training schemes. When comparing ECMs with Score SDE, EDM, and EDM with DPM Solver v3, we find that a two-step ECM, fine-tuned for 100K iterations, matches Score SDE deep in terms of FID while requiring significantly less inference cost and latency. Moreover, a two-step ECM outperforms EDM with advanced DPM Solver v3. In the context of diffusion distillation, ECT surpasses consistency distillation, CD, on both CIFAR10 and ImageNet 64x64. Notably, ECT outperforms CD without the errors of a teacher DM and without incurring additional costs. Improved Consistency Training, ICT, is a leading method for training a consistency model from scratch without relying on a diffusion teacher. ECT competes with ICT Deep using a fraction of the training compute and model size. ECT demonstrates impressive results with minimal tuning costs, showcasing advanced generative capabilities through a straightforward approach. We delve into the scaling behavior of ECT concerning training compute, model size, and model flops. ECT shows promising scalability, following a classic power law when computing resources are not limiting. By investing more computational resources in ECT, we observe substantial enhancements in generative performance. The gap between one-step and two-step generation narrows as training compute scales up, indicating improved performance. Furthermore, we train ECMS, M, L, XL models with varying parameters and flops, demonstrating that ECT effectively utilizes increased model sizes and computational power to enhance generative performance. ECT achieves superior two-step generation capabilities compared to state-of-the-art CMs while utilizing a modest training image budget. Section Summary. In this section, we conduct experiments to assess the efficiency and scalability of ECT on CIFAR10 and ImageNet 64x64 datasets, using metrics like FID and NFEs. We compare ECT with various training schemes, diffusion models, and diffusion distillation methods, showing that ECT outperforms existing approaches in terms of sample quality and training costs. Additionally, we analyze the scaling behavior of ECT in terms of training compute, model size, and flops, demonstrating that increased computational investment leads to significant improvements in generative performance, especially in one-step and two-step generation capabilities. Section: Consistency Models. In this section, we discuss consistency models, which are a novel type of generative models aimed at efficient generation in just one or two model steps without the need for adversarial training. These models, known as CMs, do not depend on a pre-trained diffusion model, DM, for generating training targets but instead utilize an unbiased score estimator. While CMs have been expanded to include multi-step sampling, latent space models, ControlNet, and additional adversarial loss, they are generally more challenging to train and demand more computational resources compared to diffusion models. Our research focuses on enhancing the training efficiency of CMs, which will lower the cost of future research and deployment involving CMs. Moreover, we delve into diffusion distillation, a prevalent training-based method inspired by knowledge distillation, to expedite the diffusion sampling process. In diffusion distillation, a pre-trained diffusion model, DM, acts as a teacher, guiding a student model to replicate the high-quality samples of the teacher model in a few steps. There are two primary approaches in this domain: trajectory matching, where the student mimics points on the teacher's sampling trajectory, and distribution matching, which minimizes the divergence between data and model distributions. While trajectory matching methods like offline distillation, progressive distillation, and consistency distillation, CD, focus on matching points on the sampling trajectory, distribution matching methods like Dream Fusion and Prophylix Dreamer use score distillation or adversarial loss to distill knowledge from a complex teacher model to a simpler student model. However, training these models can be challenging due to alternating updating schemes. Additionally, we explore fast samplers for diffusion models, which are training-free techniques that leverage advanced solvers to simulate the diffusion stochastic or ordinary differential equations more efficiently. These methods aim to reduce the number of sampling steps by analytically solving parts of the equations, using higher-order numerical methods, and correcting predictions at each step. Despite their speed, fast samplers may compromise sample quality when the number of sampling steps is too low. Furthermore, we address the limitations of existing consistency tuning, ECT, which relies on a dataset to tune DMs to CMs, unlike data-free approaches for diffusion distillation. ECT learns consistency conditions from a specific dataset using a self-teacher, while data-free methods acquire knowledge from a fixed diffusion teacher. The reliance on training data may pose challenges when such data is not publicly available. Nonetheless, exploring alternative datasets for tuning CMs could be a promising research avenue.